Well, welcome to I have the honor of doing the first session here, and I'm very excited to talk to you guys about scaling RL for coding agents and the lessons from building out a research program over the last year at Cognition. So I'm Silas, I'm part of the founding team, and also I lead research at Cognition. We're known for building Devon, the world's first AI software engineer, and also Windsurf, which we acquired about a year ago. What will we talk about today? So I wanted to tell you a little bit of our scaling journey of like 4 increasingly ambitious training runs, and in particular also how did we pick our problems and what were the bets that we took with the scale of compute and team that we had at the time. And also some challenges we solved along the way, like multi-turn training, parallel tool calls, asynchronous RL, and entropy collapse. So these are like the 4 projects that I picked, and I'm gonna just kind of like run through the journey. Kevin, 32B, were the humble beginnings of our research team. We were basically getting started. It was just like a few interns and I think 32 H200 GPUs, and we were trying to think, okay, what can we do with this amount of compute that is genuinely interesting? And the first idea that we had is just, okay, let's pick a very targeted problem and see if we can move something with RL on that targeted problem. So what we picked was kernel bench. It had just come out and was like a benchmark for writing CUDA GPU kernels with coding models. And the idea is basically you get a Python PyTorch function, and you have to write a CUDA kernel that will speed up that function. And it turned out that actually worked. So like we kind of like implemented gRPO and kind of got it to work. I think one of the like very interesting things we wanted to explore at the time is what does it look like to do multi-turn agentic training, which I think was crazy enough, like a year ago, still pretty novel. And it's kind of cool to see also on this graph that the multi-turn training outperformed the single-turn training. And yeah, I think it was kind of awesome. We were able to basically train like a state-of-the-art model on that benchmark compared to like 03, which was sold at the time, with just this like Qwen 32B like base model. One funny anecdote about like training stability that I want to share as like the one highlight from this project is we had a lot of like instability problems we had to deal with, and we found this like very interesting instability indicator that we call the not okay ratio. Basically, the model in its chain of thought would always start with the word okay. This is just like a weird quirk of this model, and it over time as the training progressed became a little bit like crazier and more desperate in its thinking. So here you see some examples. So it's like, okay, Amigos, I need to optimize this 3D tensor matrix multiplication. And like later throughout training, we'll be like, okay, holy crap, I need to get this code optimized. And the proxy for like instability was we were basically measuring this like not okay ratio. And it was an early indicator of an eventual divergence of the training run. And it was kind of like a very funny way of like how like models sometimes go wild in training. So after this, we built SWE-grep, and we wanted to become a little bit more ambitious, and wanted to build like a real useful agent that we can use in our products. And like a big thing in coding agents is finding the right files. And we thought, okay, maybe we can like solve that sub-problem and make it cheaper and faster. So the rough idea is like you maybe have like a question about a code base, like how does VS Code efficiently implement file watching? And then the objective is to find the list of files that are relevant to this question. So pretty simple, and the nice thing about it is it's like a clean, verifiable reward because you can just do F1 score against like the list of files. And so we went and like again trained like an agent using RL on this task and built our own eval that we call the code search eval. And it was very nice to see that we could, again, train a state-of-the-art model on this particular eval. At the time, it was like a Sonnet 4.5 era. And the cool thing also was that like these models, we're able to run them like super fast. So we're using like Cerebras chips. And so SWE-grep Mini in particular, you could run at like 3,000 tokens per second, which is pretty sick. And it's also pretty magic to see the model. And so we shipped that to Windsurf. And the most interesting thing here is in terms of like science and what did we figure out. I mean, a lot of details, obviously, but the parallel tool calling So the base model, and most models at the time, would call like sequentially like one tool call at a time. And I think it was around the time where like Sonnet and Anthropic had just started to do parallel tool calling. So for example, you'd see like Sonnet maybe do like 1, 2, or 3 tool calls at a time. And we really wanted to optimize the end-to-end latency of the task, which means doing as much in parallel as possible. So SWE-grep would sometimes run like 8 tool calls at a time, and that would really boost the end-to-end latency. And so here we see throughout the training run, the reward goes up, but also the number of parallel tool calls per turn go up a lot. So after SWE-grep, we said, okay, like now let's start building out real like frontier coding models that you can use for end-to-end tasks. And I'm going to highlight 2 of these. There's obviously more. There's SWE-1.5, SWE-1, but SWE-1.6 and 1.7 are the 2 latest ones that we shipped earlier this year. And at this point, we're like, yeah, like measuring like real coding evals like SWE-bench Pro and trying to see, okay, how can we just hill climb the end-to-end performance on realistic coding problems. And so SWE-1.6, we were very proud to, at the time, like match Opus 4.5 on this benchmark. And it's kind of magical to see. You know, like the same like fundamental principles still apply. You just have to obviously use more and harder data, but throughout the training run, you can massively scale the solve rate. So here you can see on like kind of our internal eval of like verifiable software engineering tasks throughout like one of these RL training runs, we improved from 52% to 68%. And the other cool thing is like the model actually learns to think for longer. So in the beginning, it maybe was thinking for on average like 4,000 thinking tokens, but this roughly doubled throughout the training run. And it really also taught us like what does it actually mean to have stable training, like a good algorithm. Because it wasn't obviously as easy as just like taking the data and like running the model. There are all kinds of collapses and stability issues. And so here you can see 2 of these. And basically what would happen is like, as we were like trying to like tune the algorithm, maybe after like 200 steps, the model would collapse. And then we would like diagnose the problem, figure out like, okay, what is the root cause? And then after we restart, it's kind of interesting to see how this almost like follows the exact same trajectory, but then at the point of collapse, now it's like more stable and can like keep going. And so with each algorithmic improvement, we could improve the training horizon from like 200 steps to 300 steps and like push it further. Another thing that I think was kind of like novel for us in this project was asynchronous RL, and how do we maximize the throughput of these like longer and longer rollouts. And basically the fundamental idea is that you separate your trainer and your rollouts, and the rollouts kind of just send additional batches of groups to the data buffer, and the trainer just kind of slurps up the data buffer as it gets full, and then when it has done a training step, it will send a weight update to the rollouts. And I'm going to come back to this a little bit later when we talk about SWE-1.7 as well. And so one kind of downside of asynchronous RL is that your like training policy and your inference policy can diverge, right? So you might receive a batch of data that's from like an inference policy that's like a couple steps old. And this is what we call staleness. So the number of steps that your inference policy is behind the training policy. And interestingly, it all comes full circle because the better you can improve the training stability of your algorithm, the more staleness you can tolerate. So especially as we were getting started, we were basically almost incapable of having high staleness, but over time we were able to push this. So here you see like 2 training runs that we compare, and the black training run can tolerate a much higher average staleness. And what this gives us is the ability to just fully utilize our inference engines. So a better algorithm allows us to achieve full compute utilization. And this leads us to SWE-1.7, our latest model. And here you can see the evals. These days, you know, you no longer do a 1D bar chart. You do these like 2D cost versus performance charts. And what I think is worth calling out here is the model does particularly well for its size class. So the base model that we trained on, in this case, was Kimi K2.7, which you see down there. And obviously there's Composer 2.5, which is also based on Kimi, and GLM 5.2, which is roughly the similar size. And for its size class, it is quite impressively high and competing at the level of many much bigger models while being much cheaper. And what were the things that it took? So I think especially as you try to squeeze the most out of these smaller models, I mean, obviously 1 trillion parameters is still big, but it's maybe not a multi-trillion parameter model as some of the frontier models. We were hearing a lot of chat about like RL is like hitting a plateau, and now it's like all about pre-training. But we wanted to see, okay, can we push this a little bit further? At this point, we're bottlenecked by entropy collapse. So obviously the juice of your RL improvements is, do you have diversity in your group? And do you have like discovery of new behaviors? And this is all measurable by what we call entropy. And so what you usually see throughout a training run is that entropy goes down over time, and eventually entropy is kind of like collapsed, and then you've hit the ceiling of your RL training run. And we were really battling with this because we just couldn't improve the model anymore. But the good news is, like, if you keep tuning your RL recipe, and you should read our technical report for a lot of the details, we were able to get a recipe that had was almost like an imperceptible decline in entropy. I think it would still decline over time, but it's like a much flatter slope. And so the nice thing is, yeah, we were able to just push the performance much more. Another cool thing is how we were training across 3 continents. So obviously we want to scale up the compute more and more. And it's just like genuinely hard these days to like find big contiguous training clusters. And especially on like the timelines that you need, like maybe you can like order them like a year in advance, but so like what we found much easier is to like find smaller slices of compute here and there, like maybe like a small cluster here, another cluster there, and the end result of this was like a training run that was operating across 4 countries and 3 continents, including Australia, Malaysia, Canada, and the US. And the reason why this, why I was saying earlier we're going to come back to async RL is, the only reason why this is possible is because of async RL. And the rough like layout of this training run is that we basically have a training cluster, which in this case was in the US. And then we have a lot of rollout clusters that are like scattered across the world. And the way this whole like system speaks to each other is that the inference clusters send the training batches to the training cluster, and then the training cluster sends weight updates to the inference clusters. And the whole reason why we can do this over the whole globe is because actually the information that needs to be transmitted is pretty sparse. In RL, like weight updates are pretty sparse, and then also the training batches are just like tokens. And with that, I'll wrap up with maybe like recapping what our philosophy with a lot of this has been, which is like we are actually not really, like our belief is it doesn't really take complex things and like fancy ideas. A lot of progress and research is just executing the simple things with care. And that I'll say. Thank you so much for having me, and I'll hand it back to Kamal.